We are going to start with a Mentimeter. Yeah, so you can just visit the mentimeter.com or scan the QR code and try to respond to the questions I have on the slides. So please just let me know if once you are on Mentimeter and once you start responding, I should be able to see the responses from my end as well. But we'll not be checking all the answers now. We'll check them later. But just look at the questions, visit Mentimeter and respond. You can either scan the QR code or you go to mentimeter.com and then type the code, the digits at the bottom right of the slide. So you have three questions on the slide. The three questions are: how many vaccines have you taken so far in your lifetime? I know some of us, you took a lot of vaccines as a child, but even the ones as a child, if you recall some of them, or you know about typical vaccines that children take, and then you think your parents would have vaccinated you as a child. And then what is your greatest worry about vaccines and vaccinations? And then if a single vaccine could protect you from a range of diseases, would you take it? So let's quickly respond to that Mentimeter before we proceed. So we would have maybe 2 to 3 minutes for people to respond. And then maybe those who join the call later would also have the opportunity to respond. But for now, let's just try and respond to those questions. Thank you very much. So if you're just, maybe somebody can help us put the link and the code in the chat so it will be easy for people to engage. So how many vaccines have you taken so far in your lifetime? What is your greatest worry about vaccines and vaccinations? If a single vaccine could protect you from a range of diseases, would you take it? Thank you very much, everyone. I'm seeing the responses. Please, let's keep sending them through. There are just three questions and you can go across all of them in within 1 minute. Thank you. Let's keep the responses coming. We have like 23 persons on the call, so I'm hoping we can get minimum 10 or 15 before we can proceed. I think we have 9 responses now. So please let's respond. It wouldn't take you 1 minute. So I don't know if anybody want to unmute and just speak as well as we are trying to respond. So Yusuf might be able to call anyone that can raise their hand if they want to just talk about their responses or just respond to the question by speaking. So the session can be a bit more engaging as well. So if anybody's open to sharing their thoughts on the questions by unmuting, please be bold enough to take the mic. Thank you.
What? I'm even saying if we have anybody in the group who have not even taken any vaccine throughout their
Oh,
life, I'll be
okay.
there to hold them tightly in case they are afraid of nurses and doctor. They don't like seeing them, or they are scared of the needle going into their body. I'll be there to hold them tightly. So I'll
Yeah,
be
yeah.
here for them.
We are ready for them. Yeah. We have to get vaccinated. Thank you. So is anybody willing to unmute and speak or respond to the questions for us here? If you are not too shy to share your responses with the group.
You can also share how much you cried when the first time you take one vaccine. You can share with
Okay,
us.
Alimat. Yeah, thank you.
Hi, everyone. Um, how many vaccines have I taken so far? Honestly, I don't know because I don't know how many I took as a baby.
Okay.
But as an adult, I've only taken the COVID vaccine. I
Okay.
think I took all three, I think. I'm not really sure anymore. And if I were to guess, as for childhood vaccine, there is a scar on my arm that I think most of us have. So whichever vaccine that is, I definitely took it.
That's for TB and BCG.
Okay, so yeah, I took that one. For the second question, my greatest worry about vaccine and vaccinations. Um, I tend to not worry about stuff like that, but if I were to mention one, it would be long-term consequences. Because,
Mm,
for instance, with COVID vaccine, we were in panic, like we as in the whole world. So we still don't know if there are any side effects to
mm,
it. And as much as we know that the conspiracy theorists are conspiracy theorists, we cannot 100% say that the vaccines we took for COVID have zero side effects. So we cannot completely debunk the worries that they
mm.
have. And if a single vaccine could protect you from a range of diseases, would you take it? I think that's related to the second question. From my perspective, if people have taken it and they're fine, sure, I'll take it. But I won't be the first one to take it.
Okay.
Yeah.
Yeah. Thank you very much, Alimat, for sharing. Thank you for being very sincere. Yeah. So I think we can proceed with the rest of the presentation now. And please let's keep the conversations engaging on the chat box. And if you're just joining, I think we'll have the link and the code in the chat box so you can also respond quickly. So this is my content. I'll talk about why vaccines and then how vaccines work, and then talk about some of the challenges and concerns associated with vaccines generally, and of course the current version of vaccines we have, and then we'll talk about what universal vaccines are. Because this is an immunology vaccines context, so I need to provide proof from what is currently known from a few recent studies, and also so the immunology people in the house can also have something to chew on that is more kind of a bit not so technical, but a bit technical. And then we'll look at what the future holds for us, and then just general highlights and then my references. So why vaccines? So everyone knows that vaccines provide protection against infection or disease. And Alimat has already said a lot about, our experience with vaccines. And those of us who were vaccinated as children, I don't know, I really don't know if my parents vaccinated me. Because I think for myself, and I think my siblings, like maybe the ones that are but I'm the youngest, so like the ones that are closer to me. I think some of us they probably gave birth to us in church or at home. Me, they gave birth to me at home. So I don't know if my parents did like those typical antenatal stuff or whether they were very consistent with getting me vaccinated as a child. But I know I have not really had any, issue with some of these typical childhood diseases. But yeah, those of us who are vaccinated or not, there is actual data to show that vaccines does provide protection against diseases and infections. Sometimes it's protecting you from the actual disease. Other times it's like preventing you from becoming severely sick. But either way, it's a form of protection. And there is also evidence that vaccines save up to 2 to 3 million lives every year. And we know the COVID-19 pandemic, which is very recent, is like our very recent proof that we can point to say, okay, look at what vaccines did during the pandemic. And with the pandemic, it totally shaped the trajectory of the of the virus and its spread. We know there are other factors that also contributed as well, because like in low and middle income countries, even though we did not have access to the vaccines on time, the impact of the pandemic in our setting, in our context, in our communities was not as severe as what we saw in the high income or higher middle income or very high income countries. Or I think there's middle income countries that's like on the higher range. So so this is just a data that just points to what the vaccine did during the pandemic. So you are seeing the graph that is labeled A. You see the um diseases that were averted by vaccines in kind of blue, and then the other ones that are averted indirectly in kind of turquoise. So you see the large number of diseases that were affected by that were averted because we had vaccines available, and then we see the number of mortality that we actually had between January 2021 and January 2022, which is were not so high compared to what you would have typically expected if vaccines were unavailable. And then on the B portion, we see vaccines, deaths that were averted by vaccination in different regions of the world. So we see upper middle income countries, lower middle income countries, low income countries, high income countries. So I think it's really interesting that low income countries, we can't even see anything on the graph. But I think if you look carefully, maybe you zoom in, you'd see there's a very tiny yellowish line at the bottom. So I think it's probably because we didn't get vaccines on time in these very low income countries. And so it was maybe it was difficult. I think as at within the time frame they were looking at, vaccines were not widely available in like regions in Africa and then maybe Asia. I think especially Africa. So maybe it was difficult to actually quantify how much deaths were averted by vaccines in our setting. But I think more recent data will probably have been able to estimate that. But I think the key thing here is that vaccines during the pandemic really changed the trajectory of COVID-19 because the experience with the 1918 flu, like 100 plus years ago, was not as I wouldn't this our experience wasn't palatable, but it wasn't as palatable or comfortable as we had with COVID-19. So on May 8th, 1974, I'm not sure there's anybody here who is up to 50. The World Health Organization declared smallpox eradicated because of a global immunization campaign that spanned several years and maybe decades. So smallpox is a very, 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 very terrible, terrible disease. I have a picture here, viewers discretion advised before I share it. But this is an interesting picture taken in 1901. Some of us would have seen it if we've attended several vaccines presentation. So it was the text is there, but it was taken in 1901. These two boys, they are the same age, around the same age. Um, the one on so that's how smallpox looks like. So who have not seen smallpox, this is how it looks like. So it's like monkeypox. If you see someone that had like mpox, but it's like I don't know, like that's serious severe disfigurement of that young boy's face and his skin and all of that. And sometimes people even die from it. But that's just the picture, evidence of what vaccines can do. So the boy on the right hand got vaccinated, the one on the left didn't get vaccinated, and then they just do like this kind of trial on them and then expose them to the virus and the same source, the same day, the same room, and you see how their body reacted or responded differently because of the vaccine that one of them got. So that's what vaccines can do. So sometimes it's not so easy to know how much vaccines protect us, except when we are comparing with when there is no protection. So we can only know how much vaccines are protecting us if we were to compare with, oh, what if I did not get vaccinated, or what if vaccines were not widely available? So humans are still threatened by numerous infectious diseases, tuberculosis, malaria, HIV/AIDS. There are emerging and emerging diseases, Marburg, Mpox that left and came back, and maybe other diseases that have left to could still come back. But I think for now, smallpox, we are done with that. Polio is almost eradicated or eliminated, but there are still like polio cases coming from vaccines and other contexts and actual infections. But so polio is probably going to be eliminated and eradicated soon. But we have neglected tropical diseases. These are diseases that majorly affect low-income countries. There are quite a lot of them, but there is Noma that cause skin disfigurement, serious disfigurement of the skin. There are several of them. Even snake bite envenoming is a neglected tropical disease, trachoma that affects the eyes, and several other diseases. And then we also have non-communicable diseases like cancers, for which vaccines are increasingly becoming available. So there are lots of research going into vaccines for cancer, although they don't work the same way as vaccines for infections, but um, they are actually efforts to make vaccines against cancers. So how do vaccines work? So vaccines leverages the immune system unique abilities. So vaccines they are very beautiful innovations and tools in the field of immunology, but they are maximizing what our immune system can already do effectively and what it can do very well. So that's what they try to maximize that they focus on leverage or maximize the immune system's ability to recognize pathogenic threats and differentiate self from non-self, to respond swiftly to agents and events that are considered harmful to health, and then to recall previously encountered agents and events from its memory. So do you have out there? So recognize, respond, recall. So if in case you ever in a position to defend what vaccines can do or how vaccines work. So you can just use this to just clarify to people who might have issues or are uncertain about vaccines or how they work. Yeah, so vaccines can recognize. That's typically vaccines help, like our immune system can recognize. So vaccines help them to recognize. So when we get a vaccine against a particular disease or infection, scientists are taking something from that pathogen, maybe the entire pathogen, part of the pathogen, the DNA or RNA of the pathogen, which they started just exploring more recently. And the immune system is able to recognize that. And it's able to know that this thing is not for me. It's not part of this, it's not self. So it's not something that's coming from your body. So it's something external to your body. So the immune system, that's why it's able to recognize it. So the immune system can recognize things from your body and things that are not from your body. So there are very, very long and interesting processes to how our immune system mature and how that it's not able to attack our own cells. So usually when cells are being, are being formed or doing development, if some cells are able to attack your own cells, then the immune system kind of just kills them and clears them out from your system, so you don't have issues. And the ones that can identify non-safe are the ones that are kind of preserved. So that's not exactly how it happens, but I'm just trying to clarify the fact that the immune system can recognize self and differentiate it from non-safe. And that's why cancers come about, because the immune system is unable to really differentiate between what is, sorry, not cancers, autoimmune disorders. Autoimmunity comes about because the immune system is not able to clearly differentiate between what is coming from you and what is external. So you just start attacking your own cells, and that's like an anomaly for the immune system. So you can respond swiftly and specifically to these agents or threats. So, and then it can also remember what is exposed to. So with a vaccine, you just have a part of the pathogen, and then the immune system responds to that. So when you actually have the infection, the immune system can remember, oh, I've seen this thing before, and then it can mount a very strong response against that actual infection. So this is just a picture I stole from World Health Organization website. I just shows you what happens, when you've received the vaccine or you've been exposed to a pathogen. So you have an antibody against that pathogen, and existing pathogen, you have an antibody. So this is the antigen where the antibody can bind to. And then you see that antibody, the portion that it binds to, it's quite similar to the shape of the antigen. And then you have a new pathogen. You don't have an antibody against that pathogen. So the immune system, if you've been vaccinated, then it can, there will be something in the vaccine that will trigger something in the immune system, like an antibody that will be able to bind to something in this pathogen and neutralize it. So if you've not been vaccinated, then yeah, you just deal with the pathogen, and yeah, or the pathogen will deal with you. If you've been vaccinated, you can deal with the pathogen. So these are just some types of vaccines that we have inactivated. So this is where you kind of kill the pathogen. You use the entire pathogen, but you kind of kill it or render it, yeah, you inactivate it. You can use chemicals, you can use different things to inactivate it, but yeah, so one of the polio vaccines actually inactivated. Then you also have live attenuated. So this one, you have the actual pathogen in you, but it is not very active. So they kind of weaken it. So attenuation is like weakening the pathogen. So I think BCG, that's the vaccine Alimat was referencing earlier that they give you in your arm. I think that's a live attenuated vaccine. You have subunit vaccine that just uses parts of the pathogen. You have RNA and DNA, like the mRNA vaccine that was popularized during COVID. You have viral vectors, and then you have toxoid vaccines. I think diphtheria vaccine is a toxoid. So this is like a toxin that is produced by the pathogen as the mechanism of protection. So what are the common challenges or concerns with vaccines? So we've probably highlighted a lot of them. And so some of the things we'll be sharing here will not be unfamiliar. So please, if you're just joining the call, we have a Mentimeter poll that you can quickly respond to. So I think there might be information in the chat box, but there'll also be an opportunity to respond later, but you can also respond if you're interested. So vaccines are effective but imperfect. So even our best friends, our family members, they can be very cool and nice with us, but there are also imperfections. So just with any other thing, there are imperfections with vaccine. I think these are some of the issues that give rise to misinformation, mistrust with vaccine, because sometimes people have this idea that, oh, if you get vaccinated, everything will be perfect. You just have this perfect life. No, life becomes a bed of roses. No, vaccines are imperfect. There are issues associated with vaccines, and I think scientists need to be more clear with that. And also the media has to be very clear that the vaccines, there could be issues associated with them that should be expected. So the very common ones are side effects. So you can take a vaccine and then you feel sick for a few days, or you have like skin reaction, you have headaches. So those are like typical. There are also adverse events that are rare. So I think maybe COVID vaccine, I think there was a link Nasiruddin shared on the group some maybe 2 years ago, last year, about a vaccine for COVID. I think that was I've forgotten the word to use now, but kind of they reversed or retracted the vaccine from use because they noticed that there were adverse events associated with it. Like some COVID vaccines, there have been events leak that has to do with, I think, some certain things that has to do with maybe the heart or respiration that comes from people that affect very few number of persons who take the vaccines. There are also people who are saying a lot of things that might not be so true about the vaccine, but there's a possibility of adverse events, and it can happen to anybody, but it is not typical, it is not common for it to happen. And then there's also limited efficacy and waning immunity. So you can get vaccinated and maybe over time you are no longer protected, and then you fall sick, and then you say, oh, I thought I was vaccinated, I thought they said this vaccine was going to protect me and all of that. So that's also possible, and that is the reason why we have booster doses sometimes. So I think for diphtheria as well, there are booster doses. That was very popular during COVID. Even childhood vaccines, you kind of take it, some of them take it 3, 4 times and all of that. So booster doses combats the issue associated with limited efficacy and waning immunity. So several factors can contribute to that, but the whole idea is sometimes your immune system is not able to, because of the nature of the infection or the pathogen, the immune system is not able to really provide long-term protection because of the kind of response that it generated initially against that pathogen. And then it's also possible that is the pathogen itself that is changing. So like mutating, that's what we saw with COVID and also influenza. Some of us that are in, more developed countries where like they give like influenza vaccines every year. I'm not sure how, um, I don't think Nigeria has like very, very severe influenza cases, compared to other parts of the world. And I don't really know much. Maybe the pharmacists can also assist if the Nigeria typically does those, seasonal influenza vaccinations. I think we might be doing it, but maybe it's not so widespread like in other countries. But influenza, COVID, they mutate a lot, right? They mutate frequently and all of that. So that also can complicate the strength of the immune response. And then there's also the issue of individual and population level response variability. So there are vaccines that if given to people in the global north or Americas or whatever, the response is stronger. But then when they bring them to Africa or Asia, they realize that the responses are weaker. So they've seen that with a lot of vaccines. I think like vaccines like rotavirus, especially. I think I can point to rotavirus, but there are also other vaccines that the responses are stronger in the global north and than in the global south. Part of the reason would be, maybe the way the vaccines were designed, it was designed within the context of people in the global north. So sometimes they just carry clinical trials, maybe third phase to come and do here after they've already designed vaccines somewhere. And I think that's part of the reason why part of this individual and population level response variability is part of the reason why the Africa CDC is, really, really paying attention to vaccination, vaccine programs, vaccinology program, vaccine design development program. We've been sharing a lot of opportunities on the group. So if you're really big on vaccine development and design, please sign up for those opportunities because there's a lot of funding for those programs, and the Africa CDC is really keen on seeing how we can develop our own vaccine so that the whole issue of population response level of response variability will be minimized or diminished. So vaccinations save life. Vaccinations save life, not necessarily vaccines. So they are vaccines, but if those vaccines are still in the storeroom, they are still in the vials, nobody will get protected. So it is vaccination itself that save lives, not necessarily vaccines. People have to get those vaccines under their skin, they have to get them, into their bloodstream or wherever, depending on the kind of vaccine, but people need to get vaccinated. And that's where the issue of trust and, public acceptance comes in as well. But I think it's something that we should be very, very aware of, that it is not so much as drugs. I think it's the same concept with drugs. It's not the drugs itself that would save people. Of course, we need the drugs, but people need to get them into their systems to be protected. So the increasing number of so that statement is just going to provide context for the next things we're going to say, because when we are thinking vaccines, we should also think of vaccinations. Because if there are like 30 vaccines and it's possible to just mix all of them together and inject me once, that would be beautiful. But 30 vaccines probably mean like at least 30, injections of vaccinations in some cases, right? And then maybe some of them have like multiple doses, and that's going like 60 or 80 and all of that. And you're like, you guys want to keep me with injections and all of that. So it's important that we think vaccination when we are thinking vaccines as well. And it's also something that informs how scientists design their vaccines. So the increasing number of pathogenic threats that we are faced with over the course of our lifetime also poses a very interesting concern. So how many vaccination and boosters am I going to have over my lifetime? Like how many, how many, how many? Like Alima was saying, just for COVID, she got like three, three doses. So I know we won't say God forbid, but imagine we have another pandemic maybe over our lifetime, maybe one pandemic and then another 3 doses, right? And then she probably got lots of childhood vaccine. So you're already looking at, have I been vaccinated like 20 times? Like this, my small, very beautiful skin, just receiving so many injections. And some of us, we get injected in other contexts as well. So, are we just going to just keep getting vaccinated for every single thing we are faced with? So those are questions that are now making scientists think of universal vaccines. One of the questions, one of the concerns, there are other contexts as well that we'll touch in the course of the presentation. But yeah, it's important that we are thinking vaccinations whenever we think vaccines. So these are important things to think about when we are thinking of vaccinations and boost and the challenges that we've highlighted. So you have multiple booster doses for numerous diseases. Pathogens can change and evolve and mutate. There are seasonal outbreaks like you have with influenza. Influenza occurs every year and you have to get vaccinated every year. So I think that's a very interesting context because you have to get vaccinated every year, and the vaccination changes with time because you get vaccinated based on the strain that is circulating. And then there are pandemics and epidemics. We saw that with COVID, and then sometimes they're like this, you know, outbreak of cholera. I think there's a cholera vaccine now in trials. I'm not sure. And and diarrhea, different all of these issues that are also caused by some of these viruses. There's also pathogen emergence and reemergence, like mpox that we thought, oh, we've won the battle over mpox several years ago. It's not so much of a big problem. I just popped up from nowhere, right? So those are all the issues that kind of make us ask the question, oh, are we going to do vaccinations? Is there a way to make things better and easier, and more comfortable? Not for people who are going to get vaccines, especially, but also in a way that, also aligns with science and how research should be done. So universal vaccines, are they silver bullet? Can they solve all these problems? Maybe not, maybe not. But let's look at how vaccines have evolved over time. So those of us who are familiar with vaccines, we know that like initially, I think the whole idea of how vaccines started was that the fact that they found out that, oh, there's a virus that infects human beings, but there's also a version of virus that infects cows. But the people who milk cows, like maids who milk these cows, they don't get infected by the virus, the version of the virus that infects human beings. So how come they are protected? Now, these virus, I think they are a bit related. Not like I don't think they are exactly the same families, but there's some relationship between them. So that's what the scientists who really did a lot of research into vaccine that is usually generally considered like maybe like the father of vaccination and stuff. That's what he noticed, like how that there's like animal to human protection for vaccines, and so we started making these vaccines. But the normal vaccines that we're familiar with is like monovalent vaccines that can protect against just one disease, like the BCG given to protect against TB, or the COVID-19 vaccine that we've received more recently. So please, if you have any question or comment, or there's anything that I need to respond to in the chat, please let me know. So those are like normal vaccines. They are conventional monovalent. So monovalent is just like one protection or one antigen or epitope. Sometimes the antigens might be multiple, but like with the COVID, I think it's the spike protein, the protein that the virus uses to get into our cells. That's the protein that is targeted. So there's also then for monovalent, we have co-administration of monovalent vaccines. So this is typical with EPI. So EPI is expanded program on immunization. So that's the program designed by the World Health Organization to ensure that children get vaccinated in their childhood, so they're protected from lots of childhood diseases. And that EPI program has saved over 100 million children since it was established. I'm not sure the year now, but maybe sometime in the 70s or 80s. So there's co-administration of monovalent vaccine. So instead of saying, let's give you one vaccine today, give you the next one, other one next month, give you another one next year. Are there vaccines that we can give together? So when a child comes for those postnatal checks, we say, okay, we can give this child up to 3 vaccines the same day. So you get one, or within the same period, just give them 3 different vaccines together and they don't cross-react, right? So that's co-administration. And then there's 10 combination vaccines. These are vaccines that different pathogens are pulled together, or the same group of pathogens. You just merge all the different protective components together to say, okay, let's merge them and give them as one vaccine. So like the diphtheria, tetanus, and pertussis, so acellular pertussis, that's the DTaP, protect against diphtheria, tetanus, and pertussis. I think pertussis is whooping cough. I think there's been diphtheria outbreak in Nigeria more recently, and we also know tetanus. That's that thing that they say if you get injured by a nail, and then you don't treat it, it could cause complication. So it's not actually the nail that causes tetanus. It's the fact that the pathogen or the organism that causes tetanus is, I think it can be in the soil and all of that. So that's why they say, okay, if it's nail, please just try and get vaccinated and stuff. Yeah. So there's also MMR, measles, mumps, and rubella. Those are 3 different infections, but they give the vaccines together in a combination. And then we have pan vaccines. So these are vaccines that cater to the same family of pathogens. So they're looking at pan vaccines currently for dengue and Zika viruses. So these are viruses, both of them are they are vectored by mosquitoes, Aedes mosquitoes. and they are both viruses. So they're trying to design vaccines. And I think another thing to point out is that they affect people in the same region, because we've talked about population level immunity as well. So when you're even combining vaccines, you have to think of, oh, these vaccines we are combining together, do they affect people in the same area? You can't say, oh, because you are trying to save, make things easy, and then a disease that does not affect certain people, you're just giving them the vaccine. That's like a huge waste. So you also have to think of, for the palm vaccines or combination vaccine, you have to think of, oh, do these diseases, do they co-infect people, or maybe not co-infect, but do they coexist? Like, in looking at the epidemiological profile, do they coexist in the same regions or communities, so that we can protect people against them simultaneously? So, and then from palm vaccines that protect pathogen families, different pathogens but the same family, now we are having universal vaccines. So let me just highlight something between combination and pan vaccines. So for combination vaccines, you have like three different vaccines, and then you're just combining them together, right? So you have three different things you are combining together, but you are sure they are not cross-reacting. Palm vaccines, you are thinking of what is common between these two pathogens, or these three pathogens, or this family of pathogens, that then we can use, that will protect against all of them. So it's not like you're making a separate vaccine for dengue and then separate for Zika, and then you are merging them. No, you're thinking of what's common between dengue and Zika, for instance, and then you are using that to design the vaccine. That's why it's pan. Then universal vaccine is quite interesting. We'll look into it more deeply, but you're not necessarily combining what is similar. You're looking at the immune system and thinking of what's the mechanism by which the immune system targets this pathogen, that we can leverage that mechanism to protect against these different pathogens. So palm vaccines, you're looking at the pathogens. So I think up until universal vaccines, we are looking at the pathogen themselves. But but with universal vaccine, scientists have taken their sight off the pathogens. They are now focusing on the immune system. What about the immune system can we use to protect against this kind of pathogens? And what can we do to the immune system that will make the immune system be able to protect against these different aspects of the pathogens, and these different pathogens, without looking at the pathogens themselves? So this an interesting quote from this paper by Rhino Rapoli and Casson. I think Rhino is a very interesting professor. I think he does viruses and vaccines related work. He's in Europe. I've forgotten the country now, but he's working with some top institution there. So in case you're looking for somewhere that will fund your PhD or master's project, you can reach out. So when numerous vaccines are used separately, their acceptability by the population decreases, as they require an increase in the number of visits, administration, side effects, and costs. So we know all the things we've talked about. So just imagine that you are going to hospital every 3 months because you want to get different vaccines, right? Or you are going every week, and then look at the side effects. Instead of having one side effect for up to four vaccines, you're having like four different cycles of headaches, and fevers, and whatever side effects that you'd experience. So this is a very interesting argument, and I think it's also we interweaves the public health angle of vaccination, right? That you're not just thinking of vaccine, you're thinking of vaccination as well, and these are all the implications of when you have like multiple vaccinations over time. And so this is what universal vaccines try to do, like I explained earlier. So they attempt to address some of these challenges by providing broad antigen agnostic heterologous protection. So the protection is broad. The protection is irrespective of the antigen of this pathogen, irrespective of the pathogen. Of course, there are families or certain kind of pathogen they are focusing on now, but I think there's the idea that it could become broader over time. But the core thing we should take note of is there's heterologous protection. So it's the the kind of antigen you are receiving is not related to the kind of antigen you are being protected from. So we know that vaccines has to be specific, right? If you get a TB vaccine, you'll be protected from TB. You get a diphtheria vaccine, you'll be protected from diphtheria. You get a COVID vaccine, you'll be protected from COVID. COVID vaccine cannot protect you from malaria. But scientists are now thinking, like I said earlier, they're thinking about the immune system itself. It's more like an host directed or host targeted mechanism of vaccination, that they are thinking about the immune system. They're no longer thinking about the pathogen. So they provide protection against a wide range of pathogens, irrespective of the antigen, without the need for antigen or epitope specificity. So the picture I showed earlier on that I said I stole from World Health Organization website, that had like this antibody and pathogen specificity, where you're seeing that the shape of the antibody is similar to the shape of the part of the antibody that binds to the pathogen is similar to the part of the pathogen that the antibody binds. But now we're not even thinking of antibodies, right? We'll see more in the course of the presentation, that we are just thinking of what's the similar mechanism by which these pathogens infect us, and how can we develop a kind of a barrier from the immune system angle to protect against this kind of pathogens. So I just wanted to highlight this very interesting mission by the Coalition for Epidemic Preparedness Innovations. Quite a mouthful, but it's CEPI, a very interesting organization that's just trying to protect every one of us from, dying or going through very difficult phases if there were ever going to be like a global pandemic or epidemic, as it were. So they have like this 100 days mission. So whether or not you are immunology or vaccines, you probably have heard of the fact that the COVID vaccines, they took very short time to develop, blah, 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 that, scientists were working overnight. I think a lot of scientists just paused whatever they were doing to design those vaccines for every one of us, for the world. So now they are thinking, if we are going to get another pandemic, do we want to go through this whole phase of, trying to get vaccines over a long period of time? Of course, COVID was really, really short. The time was contracted, but it was not so short. So they are saying, can we get therapeutics and vaccines available within the first 100 days after a new pathogen that we are not familiar with is discovered? That we say there's an outbreak of pathogen. So there's something in the field that they now call pathogen X, where they are saying any kind of pathogen at all, we have to be thinking of how can we design vaccines against pathogen X. There are lots of procedures to it, but the whole idea is, what's the shortest time frame we could use to get vaccines and therapeutics available for people in the case of a new outbreak that we are not familiar with? So there's accurate and approved rapid diagnostic tests, initial regimen of therapeutics and vaccines ready to be produced at scale, but within that 100-day period. So it's the Coalition for Epidemic Preparedness Innovations. So I'm just capturing that because I think it also fits into the context of the universal vaccines that we are talking about, because if we have these universal vaccines, then we are thinking of, like I highlighted, providing protection against diverse respiratory pathogens and beyond. So we are thinking respiratory pathogens because these are contexts in which these vaccines have been explored, one. And the pandemics, the typical pandemics that we have, they are usually respiratory. SARS was a respiratory virus. That's COVID-19. There was also a version of the SARS-CoV-2 that, no, this one is, they call it SARS-CoV-1. So there was a SARS-CoV-2, sorry. So there was a SARS-CoV-1 like in the early 21st century, like maybe 2000 and something, I think. There's also MERS, Middle East Respiratory Syndrome. So majority of these pandemic potential issues, they are usually respiratory because of the ease of spreading. They spread by maybe you cough, you even breathing safe, or you even sneeze, or you even yawn. You've already, diffused millions of the viral particles everywhere. So I think that's why these are the areas that are very, very important to scientists now. So the universal vaccines could also provide early pandemic countermeasures. So that's what I was talking about with respect to the 100 days mission, providing broad protection before strain matched vaccines are available. So there's also the possibility of getting vaccines that are specific. But before we can get those specific ones, can we get something temporary that we can manage, right? Before that. So it's important that there's early here, because I will share some findings from studies, and we are saying that the protection is not like, they're not protecting you lifelong. It's just like something temporal for now. But science is it's filled with surprises. So it's also possible that these things would evolve over time, but it's just like an early, these are early phases, and there's a long way to go. And then there's also seasonal defense. We've talked about influenza, common cold viruses, RSV, that's respiratory syncytial virus. And then, so there's also the context of them providing protection against this group of pathogens that, and then paving the way towards a vaccine that can stretch beyond respiratory context. So these are things we should be thinking about when we are thinking of these universal vaccines. For now, it's more of the respiratory, but I think it's possible that we can go beyond respiratory. And I think it's the kind of thing you can believe because of the kind of advances we've seen in science over the last several years and decades. So we'll go back to our results before I continue. But I don't know if somebody has a comment or question now, but the next part of the presentation, we just want to look at some of the studies that have found certain things with respect to these universal vaccines and what we know about them and how much protection can they provide in animal models that have been studied. So if you you've joined the call more recently, we have this Mentimeter that you can respond to. I see we have over 20 responses already. Thank you so much, everyone. So, but you can respond, and then we'll share the results in 1 minute. How many vaccines have you taken so far in your lifetime? What is your greatest worry about vaccines and vaccinations? If a single vaccine could protect you from a range of diseases, would you take it? So I think we can share the responses now because of time. So please let me know when you can see the slides of the responses. Yeah. Are we still together? Hello?
Yes,
Yes.
Yes, we are.
yes, we are.
Okay, thank you. So can we see the slides?
Yes.
For the
Okay,
question
great.
and not the response.
No, can you see the responses? They're like these tiny balls. The responses are already showing.
No, you can only see the questions.
I think you're not sharing the window yet.
Oh, really? Oh, really? Okay. Okay. I think I understand now. I wasn't sharing my screen, so I need to reshare. Thank you very much. I think you would see it now. Can you see it now?
Same.
Okay, you can see it
Yes,
now, right? Okay, great.
yes.
So these are the response. So there's somebody here who has taken at least 10 vaccines. We celebrate you. And then there's somebody who has never taken vaccines. That's nice as well. Oh, I know I got vaccinated in primary school, but I was too young to know the vaccines that they were giving us. All those immunization people that will come to school and put something in your mouth and then mark your fingers. I think most of us had those experiences. But I didn't know what they were giving. I know where they were giving, but I just know they would say, oh, there's an outbreak they need to give protect children from. And sometimes some parents would even tell you not to get those things in school and all that. And I think that's why sometimes they usually go to schools and they go to houses, they go to churches, religious centers or mosques because it's easier to just get several children there at the same time. And because sometimes at home parents may not be around and then sometimes they need parental contact, but in school they just need to tell the teachers that okay, we are vaccinating these children. In some settings, I think here in South Africa you can't just come to school and vaccinate children. You have to get permission from the parents because the school can allow, if the school allowed a child to be vaccinated, your parents can, they probably can even sue the school, can get into trouble for it. But the government also has a way of ensuring that parents allow their children to be vaccinated because of, there are just a very interesting context to it. But you can't just vaccinate children without parental consent in some settings. So this is the next slide. What's your greatest worry about vaccine? I think most persons are worried about adverse reactions. Wow. So just one person is worried about too many vaccines. So some persons 8 injections. They don't always work. One person, none at all. Interesting. Thank you very much. Then if a single vaccine could protect you from, wow, nice. Majority persons are willing to are open to taking universal vaccines. And then two, yeah, maybe few persons are not open to that. And then 3 persons are saying, well. So thank you so much, everyone, for responding. I'm really excited that we are making this session quite engaging. So I think we can move back to our presentation. So I will stop sharing now and then I will share my slides. Are my slides up?
Yes.
Yes.
Okay, thank you. So, so I'm just going to run through these studies. I'll try to make them simple as possible, but they are also not so difficult to understand. But this is the first study. BCG vaccination stimulates integrated organ immunity. So don't worry about that term. It's just something that you just have to package scientifically by feedback of the adaptive immune response to improve prolonged innate antiviral resistance. Please don't focus so much on the topic. So the studies I'm sharing, they focus on respiratory pathogens. I think that's something we've already established. So respiration, you are thinking about the lungs, the trachea, the bronchus, and all of that. So they were targeting the lung as the site in which they were trying to stimulate an integrated organ immunity. So this is what an integrated organ immunity is. It's very straightforward. It's just saying the immune response is localized. So you are targeting a particular phase of a particular section of your body for the immune response. And then you are also trying to bring together the two major arms of the immune system, the innate arm that is not specific, and then the adaptive arm that is very, very specific to pathogen and disease. So the innate arm is the first response that you get when you are infected or you are exposed to a pathogen or a vaccine. So it's just like broad, non-specific response. But the adaptive arm is more targeted and specific. So the whole idea is integrated organ immunity. The integration there is you are thinking of the innate and adaptive arm. You're also thinking of the location of the response, right? And bringing together different organs and then creating an immune response. So it's a complex tissue localized immune network involving concerted action of both the innate and adaptive immune systems along with structural cells. So the structural cells are, talking about the structural cells are talking about the location where this immune response is taking place. So the study here, they use BCG, so the same vaccine that Alimat got. And I think I need to say something about BCG vaccine for TB. It's a very, very interesting vaccine because scientists found out that children who are vaccinated against BCG, they're not only protected from TB, they're also protected from other unrelated pathogens that are not even bacteria. They're protected from even viral infections, from death and mostly deaths, but also morbidity associated with unrelated pathogens. So it's something very interesting about that BCG. So those of us, sorry, I don't know if I got BCG. I think I did. I'm not sure I did. I think I don't have that mark on my arm. But those individuals that got BCG as children, BCG probably protected them from other infections that they do not know about, right? That's what science has found. So I think that's why they conducted this study to just see. And they found out that BCG vaccination in mice could also protect mice from COVID. So this is what they did. So they probably just looking at the mechanism that would allow, antiviral effect that is mediated or that is mediated by BCG vaccine against SARS-CoV-2. So that's the virus that causes COVID-19. And they found out roles for CD4, which are helper T cells in mediating the protection. So this is the integrated organ immunity I'm trying to explain. So you can, maybe when you are looking at the slide, you can get more understanding, but it's just showing you the mechanism by which the adaptive and innate arm of the immune response are working together. So the innate arm is non-specific, and I said it's the first response. So, but then eventually adaptive arm would kick in. It usually takes, innate arm is almost immediately. Adaptive response can take 1 to 2 weeks. So the idea is this BCG vaccination, trigger the innate arm typically, but then within 1 to 2 weeks, it also triggered the adaptive arm. And they realized that once the adaptive arm has been triggered, it was providing feedback to the innate arm, and because this is happened within the lung or is respiratory, they found out that these mice were also protected against COVID-19. So they also found that the mice were also protected against COVID-19 by this working together of the innate and adaptive arms of the immune system. So I said the innate comes first, and then the adaptive kicks in, and then eventually the adaptive starts providing feedback to the innate arm that allows it to continue, because the innate arm that would allow somebody getting a BCG, allow mice getting a BCG vaccine to be protected from a different pathogen entirely, in this case SARS-CoV-2. So this is basically what they did. I'm just going to focus on a section, but they just vaccinated the mice with the BCG, and then they infected them with a strain of SARS-CoV-2 that they could use in mice. And you see, at 7 days, they were just measuring the weight. So I'm just showing this one part of their experiment because of the nature of the presentation. So you see that at 7 days after vaccination, the weight of both mice that were vaccinated, BCG intravenously, that's the IV, and mice that were unvaccinated, that's the blue line, there's no change. At 14 days, there's no change. At 21 days, you see that the mice that were vaccinated with BCG, they've recovered. Their weight is almost as if it did not change at all. This is because the adaptive arm of the immune system has kicked in, and then is now providing feedback to the innate arm of the immune system that allows that protection, that non-specific protection to be possible. And then you see also at 28 days, at 42 days, the mice that were vaccinated with BCG did not have weight loss compared to mice that were unvaccinated. And let's know that the context of the infection here is SARS-CoV-2, not tuberculosis. So that's something they realized, that BCG vaccination will protect mice against challenge with SARS-CoV-2 virus. And it's based on that integrated organ immunity that we just talked about. And there is another interesting study. This study was published this year in 2026. I think it was published in February. And then here, what is very interesting about here is now they're not even looking at, the previous one they look at BCG. BCG is a vaccine against TB, and they were looking at mice. Now they're not even looking at the vaccine against a specific disease. They're just looking at a randomly designed vaccine that had TLRs. So TLRs are toll-like receptors, but that's not what's important. The interesting thing is they had like TLR ligands. That's like molecules that could trigger the innate arm of the immune system. That's the non-specific and early response arm. And then they had an antigen, just an interesting antigen. It's not an antigen that protects against a disease. So it's a model antigen that they typically use in this kind of studies because it's easy for you to measure, to kind of really quantify the level of the immune response because of the kind of studies that have been done on this antigen. So it's not an antigen that typically protects against disease, but it's an antigen that can provide that specific immune response from the adaptive arm. So they found out that a mucosal vaccine, so the previous study they did intravenously. So they found here that mucosal, so that's probably you're inhaling it, right? It's given via the mucosal route, maybe your eyes, maybe your nose, and all of that. But in this case, it was through the intranasal route. So they could explore the dynamic interplay between innate and adaptive immunity to stimulate an integrated organ immunity and protect against diverse pathogens. So the context here is also respiratory. So the TLR effect is innate and non-specific, and then the antigen effect is specific and adaptive, involving the T cell. So this was what they did. They vaccinated mice with this antigen formulation that had the innate arm and then the adaptive arm, the molecule that would trigger the innate and adaptive arm together, and then they measured the immune response against different pathogens. And then they also noticed that it could also protect them from allergy involving dust. But these studies were on mice. So this is just like looking at the different components that they use and just trying to provide explanation. But I just wanted to highlight that oval domain is just a model antigen, and it's unrelated to the pathogens that were used during infection. And this study, again, is intranasal. It's not intravenous. And that is why the whole idea of universal vaccine is leaning further into the possibility of it being used in humans, because intravenous vaccines for humans is very, very complicated, and it's not something that is advisable because it could just cause a very big problem if there's like dissemination of the pathogen, and then the immune response can be so strong and then the person can die. And there are just lots of complications. So that's why they I don't know if they give any vaccine intravenously. I think they do, but it will be maybe vaccines that are like really, really inactivated and all of that. Yeah, and all of that. So, but I think the main idea, I think they do give some vaccines IV, but the kind of vaccine is very important, right? So, but the main idea here is they are now giving this vaccine not via the intravenous route, but intranasally, right? Via mucosal route. So this was what they also found out, right? So the similar thing, they gave these mice the vaccines to these mice, and then they challenged the mice with also COVID, right? With SARS-CoV-2. And then they see that at 21 days, initial study, they did 7 and 4 days, 14 days, right? I think it's the same group. But now they already know that, okay, it will take up to 2 or 3 weeks for the adaptive arm to kick in. So they see that at 21 days, these mice that were vaccinated and then infected with COVID, they didn't experience much weight loss compared to those that were not vaccinated. Similar thing at 42 days and at 3 months. So they did not do the study beyond 3 months, but as you see at 3 months, like the difference is not so much compared to at 21 days. In fact, the other mice were already recovering. So it's possible that this protection can only be short term. But the very interesting thing is that you are getting vaccine from a random model antigen, not so random. We'll talk about why it's important to choose the antigen very carefully, but it's just like the antigen does not cause disease, but it's providing protection against a specific disease. And also it's just because of that integrated organ immunity that engages both the innate and adaptive arm of the immune response of the immune system to provide that protection. So they also looked at bacteria that could also cause respiratory infection. They look at Staph aureus. They looked at Acinetobacter baumannii. Sorry, microbiologists, if I murdered that name. And they did the same thing, 21 days, 42 days, and 3 months. And they saw that the mice that were vaccinated had much lower load of this bacteria compared to mice that were not vaccinated. So we are seeing the difference, fold change, and all of that across the two bacteria. So this is now virus bacteria, but it's still within the respiratory context. And then they did something else. They primed these mice with influenza, gave that same vaccine, and then infected with the SARS-CoV-2, that's the virus that would cause COVID, and they also saw protection in the same across, like they saw in the other context and all of that. So I think the whole idea here is that you have an antigen. We talked about antigen that is agnostic, and the protection is broad and heterologous, providing protection against specific diseases in a kind of, providing protection against specific infection or diseases in a non-specific way. Because now you're not thinking of the pathogen itself that you're trying to protect against. You're thinking of how do these pathogens affect humans and how does the immune system respond to them. So interesting why they were looking at some of these pathogens like COVID, like influenza. So I just wanted to highlight that. I didn't want to complicate the presentation, but I just want to highlight that one reason why the respiratory route or respiratory pathogens were being considered is because we know, with like we highlighted before, that if we're going to get a pandemic, like we've seen with previous cases, it's likely going to be something respiratory that will cause pandemic. But also some of these viruses, their incubation times are so short. So with COVID, I think incubation is maybe just a few days, and then the infection has already kind of just taken over your respiratory system before the adaptive arm of the immune system can really kick in. So it's so short that it doesn't give the immune system much time to provide that very strong response, right? So the incubation time is so short for like COVID and also for influenza. So that's the problem. And also another concern is these viruses focus majorly on the respiratory system. So they don't really spread to other parts of the body much. There are studies that can point to, okay, maybe COVID can be found in maybe affect brain, affect heart, or blah, 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 but it's largely within the lung. So because it's kind of there's that it doesn't disseminate, it's just kind of considered on the lung. It's also difficult for the immune response to the immune response that can be provided can only be focused on that lung. So you can't get response from other parts of the body coming to the lung and all of that. So these are issues that they were thinking about that made them to say, okay, let's explore this integrated organ immunity in the context of the lung. So other typical pathogens, they can have like longer incubation time. So if it's going to take like more than 1 week, then before the infection will really kick in, the adaptive arm would have been triggered, because it takes longer time to trigger the adaptive arm, and then so you can get a stronger response. But because it's so short, before the adaptive arm can be triggered, the infection is already established, right? And it's also localized, very localized within the lung. So they're thinking of, okay, can we make our approach also localized to the lung, and can we engage both the innate and adaptive arm of the immune system to attack or to provide protection against these very difficult pathogens? So looking ahead, so this is a quote from one of the papers I also consulted. So it says we must think outside the box to make next generation vaccines that elicit immune protection against viruses that survive in human populations because of their ability to significantly remain outside the full protective reach of innate and adaptive immunity. So that's what I was trying to explain, that these viruses, typically respiratory viruses, they have short incubation times. They are localized to the respiratory system. So it's difficult for the innate and adaptive arm to work together because of that short incubation time, and also because of that localized effect or impact of their infection. So you typically will not see COVID in lung. That's why COVID diagnosis, you use PCR, you use like the genetic component to diagnose COVID, because it's not something that you can say you want to just draw the blood and measure it in the blood. So that kind of just limits how much how much interaction the immune system can have with these pathogens. So if we succeed at designing vaccines that are truly universal for humans, whether within or outside the context of respiratory illnesses, there's also the public health hurdle, like we highlighted earlier on, of getting buy-in from members of the public. Well, people want to take these kind of vaccines. I'm glad that several persons will be open to taking universal vaccines when it becomes available. But we need public trust, we need acceptance, we need engagement, we need follow-through to ensure that the vaccine vials in this context, or maybe any vaccine at all, can translate into protective vaccinations for individuals. But until then, there are still several questions scientists have to clarify. So we said in this case of mice, they use OVA, which is a model antigen. And the reason why they use that, because this is an antigen that has been extensively studied, and we know the kind of response it generates. So it's easy to measure. But we need strong response from the adaptive arm. In this case, T cells that can provide feedback to the innate arm and sustain the innate response. Because the innate response is early, is also short-lived, right? So we need it to be sustained over time. So what kind of antigen would they use if they're going to use this kind of vaccines in humans? You probably don't just want to use any random antigen. right? You don't want, I mentioned before that BCG can provide protection against heterologous unrelated pathogens, but maybe do they want to use BCG? Maybe, maybe not. Or maybe are they going to think of a model antigen for humans? Maybe, maybe not. And then what's the route of administration? These were mine. So it's easy to just say you're going to just use aerosol sprays and just spray it into the nose and then to get to the lung. But humans, we have more complicated and all of that. So are you going to say you're just going to use intranasal vaccines for humans and then it's going to work the same way it worked in mice? And then the number of doses for this study, the second study that they were looking at, the bacteria, and they're also looking at viruses. They gave the mice 4 doses for them to see any significant effect of the vaccination. So are you going to say we are going to give human beings 4 doses, right, for these vaccines? I think Ibrahim did a presentation on one of their studies some time ago, maybe last year, that they were just trying to look at. One of the things they looked at in the study was about how people how people complete their vaccinations over time. I think they're trying to provide recommendation on, I think, the malaria vaccine, how to ensure that a lot of persons get it. And then the multiple doses for vaccine is a big problem because people that don't complete their doses. So are you going to say this kind of vaccine will be available and then I have to take 4 doses to be protected and then I have to be going to the hospital like 2 weeks or 3 months and all of that? So that also poses a challenge. So is it possible to reduce the number of doses? What route of administration do we use and what kind of antigen will be able to engage the adaptive, more specific, and long-term protective arm of the immune system to, effectively provide feedback that the innate arm of the immune system needs to provide that kind of protection. So we need all these questions to be answered and possibly more questions if this innovation would eventually make it into humans. So I'm wrapping up already. Highlight of the presentation: vaccines can protect us from deadly pathogens, but there are just so many pathogens that getting vaccinated against them all is both impracticable and tedious. Scientists think designing universal vaccine will solve these problems, especially for certain pathogens that have mastered the art of shape-shifting. They still have a long, long way to go, but we'll be here to cheer them on until they do. So thank you so much for listening. These are my references, and I'll welcome contributions and questions now. Thank you.
Thank you very much, Welt, for the presentation. I said initially from the start that Welt is really going to enrich us with a lot of information, and we are going to be going home with goodies and takeaways. Walt, please, can you go to maybe second to the last slide where you have some questions so that if people have idea, specifically,
Okay.
yeah, so they can say 1 or 2 things, and the questions you've asked, they can also give an answer to it.
Yeah, please you can read the question. I'm trying to go through the chat, but please you can also help me with the questions if
Yeah,
somebody
the
has asked a
first
question
question,
before.
what model antigen would provide long T cell centric response, driving protection and sustaining innate immunity? The second question, route of administration. The third question, number of doses.
Yeah, thank you, Yusuf. So I think these are questions that we may not be able, we can just comment on generally because these are questions that we are not sure about yet that scientists need to tease out. So I was thinking maybe somebody had a question in the chat or something. But I think
Yeah,
the vaccines people here and immunology people, please, Habib, Abdulafiz, you guys can comment, and our pharmacists as well can also pour in their thoughts. And yeah, thank you very much. Thank you so much, Yusuf.
yeah, maybe I should start mentioning name. I know Taufika is here. Taufika. And I can mention the chief himself, the triple chief, Nasruddin. I,
Hi everyone.
I,
Okay, so I don't have a question, or should I say, I'm just going to be adding to the questions that Worth has already listed. By the way, that was a very good, beautiful presentation. Thank you very much. As everyone has been mentioning in the chat box, you've really um, given us just a bit of your wealth of knowledge. Thank you so much. So I think in addition to all of these questions, another question that probably need to also ask, and going in line with what Alimat mentioned at the beginning of this presentation when she was responding to the Mentimeter post, there is also the concern about the long-term effect. I mean, we're still not very certain about the very long-term effect of the existing, vaccines that we have around. So by the time we then have maybe universal vaccine that, we just, I wouldn't say it's blind, it's blinded to antigens, just like you've mentioned. It's going to be a question of, okay, what would be the long-term effect that would eventually come up later. So that, I think that's also another question that needs to be answered. Thank you.
Yeah, thank you so much, Abdulaziz. Yeah, that's very true. I think I did not even think about long-term effect when I was prepping, but I think when she mentioned it, I was like, yeah, true. And it's even difficult to even measure long-term effects because it will take time. Like I know scientists want to design studies in the future, maybe 10 years, 20 years to see people that took COVID, how are they faring now and all of that. And there are also issues, so many things flying around with this cervical cancer vaccine. Yeah, cervical cancer vaccine as well. So it's the long-term effect is very, very important. And it's also difficult that it's not something we have to wait for it, and people have to take the vaccine for us to know how it will affect them. Yeah, thank you.
Yeah, exactly, and that's one of the major challenges to a major challenge to the to people getting vaccinated.
Mm,
Scientists are very ambitious. They can think about what would happen. What they can think about something that would um, maybe give us some sort of protection or be beneficial for the next 20, 50, 30 years. AI is one of it, kind of, but the long-term effects, we are not very certain about that, and people are concerned about it as well. So, but yeah, it is what it is.
yeah, thank you very much.
Thank you very much, Abdulaziz, for your contribution. If we've paid attention to what slide, there is a particular picture where shared maybe in the third or fourth slide, what should not go to the third picture. It shouldn't go to the slide. But I want to ask, did we take note? What is the age of the two children in that picture when the picture was taken? Raising up their hands. Read one below. The floor is yours. Below, read one. The floor is yours.
Sorry, I got logged out. I don't know why. Yep.
Okay, you don't have
So
any question?
now I have like a contribution like from the question about the model of antigen that could provide long T cell centric response. So as of recently, I think recently I heard about because like what's mentioned in the presentation, uh, using unstable antigen or like a surface proteins antigen like a spike in COVID-19 and uh, some other viruses and the likes. So recently they found out about nucleocapsid N protein,
Mm,
so which is the primary model antigen identified recently, and it's driving a long-term T-cell centric response while still sustaining in its immunity as well.
mm,
So the issue is to uh, find exactly what is highly conserved across variants and family. So this will enable scientists to design a long-term and term and universal vaccine. So having a conserved region among these viruses will help. So, but however, in cancer, so it's more easier in cancer than in vaccine, because recently they several research that are going on designing vaccine that are specific to each cancer. And these vaccines are targeting the tumor antigens itself, which are called neoantigens or neoepitopes. So they are the epitopes presented by the tumor or the cancer-causing protein itself. So targeting those neoantigens make it easier to specifically target the cancer. And we could think of this like having different cancer and having different causes of this cancer, maybe the protein, the mutation, maybe like, for example, as I'm working on KRAS, they are also in breast cancer and they are also in other cancer types as well. For example, the KRAS mutations, neoantigens, they are causing pancreatic, colorectal, lung cancer, mention most of the cancers type as well. So targeting that could be a universal as well. Another thing is that there are also other proteins that are causing different cancer as well. So picking those neoantigens, because there is an mRNA vaccine that picked all the neoantigens, maybe like 20 different neoantigens, and tested them. So 20 different neoantigens from different proteins causing mutations. So this could help as well in designing universal. That's why I said it might be easier in cancer to design a therapeutic vaccine, but in viruses, it's just to have a conserved protein region among all these viruses, which could help for a long-term T-cell immunity. So and about the long-term adverse effects of this vaccine or whatever drugs we are taking. I think people who are looking for protection, they're the one who are more concerned about this. But people who are looking for therapeutic aspect of it, they just want they want objective response rate and maybe median progressive survivor, maybe 1 year or 2 years or 3 years or 4 years or 5 years. That's what they are looking for. So people who are really sick are looking for something that can still extend their life to next 2, 3, 4 years. So whereby people who are not really sick are worrying about the long-term protection, adverse effect of whatever they are taking. So and that makes me wonder, like, make it more interesting. Like, may we not be sick that we need urgent,
I mean, thank you.
urgent protection. So that's all I have for now.
Thank you, Bello Ridwan. Akin, you ask Susan.
All right, good evening, everyone. So I
Evening.
just have a question. It's not like, okay, so for universal vaccines, that's where like I'm concerned, because okay, for pan vaccines, it said something about diseases that have related mechanism of actions can be, and that's why I understand it could be cancers and all. But are there any recommendations for you? Because regarding universal vaccines, from my understanding, does it mean they are going to be treating at all forms of diseases? And also, knowing that diseases have different mechanism of action, how is the like what's the is there I'm just trying to like I just want to know like what's their propositions or something regarding how they are going to want to target the different, because they have different causes and mechanisms. So like how will a vaccine now be able to treat because some of them, most of their causes are not even related, and so except for the pan vaccine, I understand that those one maybe these that have close, relations in their mechanism, but then for like all forms of disease, I'm just thinking like How, yeah, that's my question.
Yeah, thank you, Susan, for your question. So I think I just put up the slide that discusses what you're asking about. So pan vaccines are largely pathogen families. So similar pathogens or pathogens that belong to similar families. So likely the mechanism of infection will also be similar with universal vaccines. So maybe you should forgive the usage of the universal term, but the idea is you are no longer focusing on the pathogens. You are now focusing on the immune system itself. And let me not put it that way. We are focusing on, the immune system itself and how does the immune system fight this pathogen. So if the immune system has the similar mechanism against XYZ pathogens, then we can design a universal vaccine for XYZ pathogens. I can't say if it will be possible to have one vaccine against all diseases. That would be too much of a stretch. But we can have one vaccine against pathogens that infect the immune system, probably through similar routes. It's possible. Maybe in the far future, we could extend beyond that. So the universal vaccine is where we are talking about mechanisms, especially. I think with the other vaccines, I did not talk so much about mechanisms. It's universal vaccines that has like more of mechanisms. So if this virus or bacteria infects people via the respiratory route, then we can build a barrier in the respiratory route that protects against all of them. And that barrier is not initiated by an antigen specific to any of the pathogens we are targeting. So that's kind of the difference between the two of them. So with the other vaccines, of course, the mechanism is important for all pathogen, for any vaccine. But universal vaccines, you're not thinking about the pathogens much again. You're thinking more about the immune system and how it responds to those pathogens, which in most cases would be unrelated. Like we saw in the examples, there was bacteria and viruses that typically do not have any relationship between themselves. Yeah. I don't know if that's clear.
Thank you very much, Walt. But let me read out some funny things in the chat box. At least maybe probably we have an answer to it, or if we don't, we're just going to laugh away and go home with that. From the chief himself, Shakir Atoyebi, hypothetically, if a negative side effect of a vaccine would only become apparent 200 years after it was administered, is that effect really important? That is from Shakir Atoyebi. And Abdulhafiz responded, how do we know it's going to be 200 years? That is from Triple Chief himself, Nasru. He's saying, considering the eventful withdrawal of AstraZeneca COVID-19 vaccine from the market after use, would people be willing to take a shot for other pandemic in the future? What would be the fate of those that have survived the both of the vaccines effect in the future? These are some of the questions or some of the discussion in the chat box. If we have any comments to that, we have the attendance sheet in the chat box. You can please kindly fill the attendance sheet and copy the link. That is very, very important. You copy the link before we end the program. If we have any of the members or the founder members online who have one or two things to give as message or have some information to give out or had any information or question to Wealth, please kindly speak.
Yeah, I think Abdulhafiz and is raised, and I think Ridwan as well. So maybe they can come up.
Abdulhafiz, the floor is
Okay.
yours.
Yeah, sorry. I was going to add a comment to the last question from Suzanne. Just to add to the point that Wealth mentioned in responding to it. I think you should just look at universal vaccine as in this context. I mean, just like I mentioned in the chat box that somewhere in the chat box that ordinarily, without any intervention, the body would eventually heal from any kind of disease if you give it enough time. But the main issue is, there are challenges within the time that you are, the body is being challenged within the time that you are giving it the time to heal from a particular infection. So, and that's where the problem comes in. But if there is no any issue and there is an infection, if you give the body the time, it would, it will eat by itself, which actually shows that the immune system is actually an interesting thing. And I think that's exactly what scientists are trying to look at now, that if the body has a way to undo any form of disease whatsoever by itself, by whatever mechanism, if we can tap into that kind of knowledge, we could be able to come up with something that is similarly universal. I think looking at it in that context would make it make sense as to what they are looking at this year. Thank you.
Very much, Abdulhafiz. Ridwan, Bello Ridwan.
Yeah, thank you. So, about the route of administration, so for this version, one thing is that there are combination strategies normally that people are trying now. So first maybe intramuscular, then intranasal as well. So this combination has been even I think recently in one lab they're trying to see for maybe HPV vaccines. So where they are trying to combine different strategies, and it's really works and like show more efficacy than just only one route. So one is maybe they start with intramuscular and boost with intranasal as well. So those are the another means of increasing the efficacy or the route of administration, like which might be different from the spray option. It's available for the universal. So another thing is what Abdulhafiz just recently mentioned. Sometimes I think it's other way around. Is if you leave the body, because initially the immune system has already been compromised. That's why the disease take effect in the first place. And it's difficult for the immune system to correct itself. So when it go rogue. So because naturally, before any disease sets in, the immune system has been fighting, going forth and back, fighting really hard. But when it's compromised that it can win the battle, that's when this disease sets in. So the other way around is that look at this as the way the initially, before the disease set in, how is the immune system are supposed to fight? And that's why the vaccine is coming intact, in place, is to see how these antigens, how the immune system can recognize the antigen as a threat. Because they didn't recognize them as a threat initially, that's how the disease comes in place. But how they now introduce the antigen exogenously, externally, to see if the body will still recognize this, for the immune system to recognize them. Now putting all these antigens together and see how they can recognize of the same strain, of the same or maybe of different strain. That's how the vaccine and the immune system works. So because before any disease setting, that means the immune system has been compromised. And there have been both the innate has been damaged, and before getting to the adaptive, where they had no power anymore to fight so the basis of any immunotherapy is to train the immune system back to fight what they didn't recognize in the first instance. So, thank you.
Thank you very much, Ridwan. Do we have any comment from the founders or any other person? Any other questions?